Welcome to the February 4th video lecture for POL 101. We're going to pick up where we left off in class on Wednesday. If you remember, we just watched a couple of videos. The first was a video of a guy named David Deutsch telling us about what makes good science. Second was a video of Tucker Carlson's show where they were discussing how immigration was likely to affect economic outcomes in the United States. Two things that I want to review from the Deutsch video before we move on. The first is Deutsch's definition of good science requires that we come up with good explanations. And I just want to highlight that there are two elements of a good explanation that Deutsch thinks are important. The first element is that when we generate a hypothesis from a theory or from an explanation, when that hypothesis turns out to be false, good explanations blow up the entire theory. If we're wrong, we can't subtly change the theory in order to incorporate the failed hypothesis. We actually need to go back to the drawing board and restart our theories. And that's very important. And we saw in the Carlson video how reluctant the host was to change his theory about what immigration means for the United States, despite the fact that many of his factual predictions were rebutted by his guest. The second element that Deutsch discusses that I think is equally important is that good theories, whether they're theories of hard science or whether they're theories of social science and behavioral sciences, will have multiple hypotheses that sort of come at the theory from differing angles. Deutsch uses Karl Popper and some quotes from Karl Popper's work to animate his discussion. Karl Popper also said that the truth is most likely to exist at the confluence of multiple streams of evidence. And what he means by that is the more predictions we can make about different things, different implications of our theory, the more certain we can be that the theory is true as we test those implications. Okay. So then the second thing that we wanted to take from the Deutsch video was a review of the exercise that I did on the board. This is known as the logic of comparison, right? This game that I played on the whiteboard during the video. It helps demonstrate how you can use case selection to help you infer causation when you see patterns in independent variables and dependent variables. Let's break this down just a little bit. So we talked in the first half of this lecture about how theories are dense explanations for how independent variables change dependent variables. So all of our theories imply that there are certain variables at play, and particularly independent variables that matter. And then in the social sciences, when we think about what these variables are, we also need to imagine the context in which we're going to measure them, and we need to tailor our measurement strategy to match the context. So one of the examples we've been going through quite a bit is this idea that we have a theory that studying affects grades through the mechanism of improving recall. So in this case, we have a theory about how studying affects grades, and we have a variable here, an independent variable that measures the number of hours that students spend studying. This variable probably doesn't need a lot of contextualization, but when we get into the social sciences, we can see that this might matter, right? Say that we think democratic countries are likely to be richer than countries that have dictators. We might then hypothesize that the more people who voted in 1950, the richer the country will be in 1980, or the more people who had the right to vote in 1950, the richer the country will be in 1980. So if that's true, we might want to know a little bit more about the country where we're measuring, right? If we're in a place like the United States where there is a pretty sophisticated series of voter identification laws and voter registration systems, we might just go to the voter registration system and figure out how many people are allowed to vote. But as we saw in the earliest slides in this lecture, in places like Afghanistan, these voter registration systems don't exist, and so we may need to go from village to village counting purple fingers, because we know that in the context of the Afghan election, the purpled finger means that a person voted or was eligible to vote. So when we go back to this chart then, what we see is that these columns that are to the right here are filled in with our theories and the variables that we think matter for these theories, right? So if we're going back to our grade point average example. Our theory might be that studying matters, and therefore we'd fill in that your theory column head with something like hours studied. An alternative theory that we discussed before might be that how wealthy a student's family is matters for their GPA, and then our alt theory number 1 might get filled in with some variable that relates to family wealth. Alt theory 2 might have some measure of a student's mental health. Alt 3 might have a different operationalization. And then, of course, we see here, this is where we'd stick our dependent variable or the GPA. And then most important for the exercise we're going through here is that the rows, each of these rows, tell us where we're taking the measurement, right? And to make this as simple as possible in an introductory sense, we're going to talk about just 2 cases, case A and case B. These might be people. If we want to know what party people vote for, then we would fill in the dependent variable in each row with Republican or Democrat if we're in the United States. These might be companies, and we care about what makes the company profitable versus what makes the company pull a loss, and then our dependent variable might be the amount of money that the company made last year. Or they might be countries. Why are some countries rich and other countries poor? And then our dependent variable might be GDP per capita or the amount of wealth that the country generates or something else. But this is where we would fill in our cases. So let's say that we have 2 cases with different outcomes, right? 2 countries, one of which is rich and one of which is poor, 2 people, one who votes Democrat and one who votes Republican, and we have our theory about what independent variable might explain variation in the dependent variable. To review from the explanation from the video, right, we know that our theory is wrong here. Why is our theory wrong here? Okay, hopefully you've said that you can't explain variation with a constant, right? Our independent variable doesn't change, but the dependent variable does change, and it's not possible to have a theory that suggests that a dependent variable changes without an independent variable changing. Okay, so now we have things sorted, right? Our theory seems to vary in the same way that the dependent variable varies, or the independent variable that's important to our theory varies in the same way that the dependent variable changes. Now, quite a few policy explanations, whether you see them on the news or whether you hear them from politicians, begins and ends here. The independent variable and the dependent variable match, so we must be right. Examples of this, right, might be tax rates and growth. We find some period of history where the tax rate matches our expectation for growth, or we find some period of history or a time in which a state sent a surge of soldiers to counter an insurgency, and the insurgency ended. And because there's an association between the tax rate and growth over this period, or because there's an association between the number of troops that are in a country and how strong the insurgency is, the claim is made that we have identified causation, right? That the change in the tax rate changed the growth, that the change in the number of hours the students studied changed their GPA, that's what's going on. But of course we can't know this, right? We can't tell. It's very possible that there's an alternative theory where the independent variable matches the dependent variable just as well. So here again, if our dependent variable is GPA and we have one student with a high GPA and another student with a low GPA, and then we measure how long the student spends studying, and the student with the high GPA spends a lot of time studying, the student with the low GPA does not, we might call that a game. But we couldn't, because it's possible that the student who studies a lot also comes from a rich family, and that the student who doesn't study very much doesn't come from a rich family. You might imagine how these 2 things might even be connected, right? The student from the rich family has their parents paying for their tuition, and therefore they don't need to go to work, and so they can spend more time studying. And what's really happening here is that it's the student's wealth. So this is what's important, why it's important to do a literature review, why it's important to list out all of your alternative theories, why it's important to derive hypotheses from all of your alternative theories, right? And what we've laid out here in each column is a hypothesis. We expect that the variables in the your theory column should be yes and no. alternative theory 1 would expect that the variables in that column should be yes and no. But unless we lay out all of the plausible alternatives, we don't know that we've controlled for alternative explanations. So this is what we'd like to see. You'll notice that the variables in the your theory column vary in a way that matches the variation in the dependent variable, but that there's no variation in the variables predicted by or implicated by the other theories. So in those circumstances, we have a constant that can't predict variation in the dependent variable. And in this case, if we've actually listed out and tested all of the plausible theories that explain our dependent variable, all of the plausible reasons that a student's GPA might vary, for example, we've shown that there's no variation in the alternative theories. There's only variation in our theory. Our theory's independent variable. Then we're sort of forced to admit that our theory must be correct, that the hypothesis of our theory is the only one that's supported here, and that our theory is the most plausible. This layout is called the method of least difference, right? You have two cases for whom the outcome is different, but they look very similar, right? You can imagine this as a BuzzFeed article, right? You've got two people, and this one secret will make you skinny, or this one secret will make you rich. And they take two very similar people and they treat one of them with their secret and the other one does not get the secret. And then the person who gets the secret turns out better, right? So the method of least difference. We take two cases that appear very similar and we demonstrate that their outcomes are different because of one crucial difference between them. Other examples of this, you might choose France and Germany as countries that are very similar. They're next door to one another, but they're both rich. They're both European. You might argue that some difference that exists between the two of them could only be caused by something other than their geographical location or other than their wealth, because these countries are similar in those ways. Notice that you can do this same sort of reasoning in a different way, right? Here we've left out the alternative theory 3. We can do this logic in a different way. This is the method of least similarity, and what you'll notice here is that the dependent variable doesn't vary, right? It is a constant. And in this case, the only independent variable that is also a constant are the independent variables that are predicted by your theory. All of these other independent variables show variation. So in this case, you would say you can't predict a constant with variation. So in this case, what we've done is we've selected two cases that are extremely similar, but where the outcome is, extremely different, but where the outcome is the same, right? We have two people who are from completely different walks of life who both vote Republican. So therefore, the reason that they both vote Republican must be the similarity that they share. We choose two countries from opposite sides of the world that both become democracies. And because these countries are so different, we know that if we find the thing about them that's similar, that must be the thing that explains why they are both democratic. Okay, the logic of case comparison in pairs, where we only have a case A and a case B, this is fine when we're looking at binary outcomes. But with intuitively continuous variables, at the individual level, it's pretty awkward, right? I mean, I've just thrown in some numbers here that are totally random, right? But it would be hard to tell, for example, if the difference between 12 and 16 could possibly theoretically make the difference between a 54 and a 48. Think again about our students and their GPAs, right? If one student gets a 3.0 and the other student gets a 3.5, and the student with the 3.5 students are ever so slightly richer and they spend a little bit less time studying, it can become pretty confusing to suss out which of the differences, what sort of variation in our independent variables actually makes the difference. And over time, you end up with these spreadsheets that have massive, massive numbers of cases, and they have values for all of these potential independent variables. And you're left looking, searching through all of this data for patterns. Patterns in what you might expect the independent variable and dependent variable relationship to be. And this is when we need statistics. Okay, so there's not going to be any statistics on our exams, but we are going to be reading papers that include statistics. You're given statistics as supposed evidence for political theories or political cause and effect on the news or in political advertising all the time. So we need to develop an intuition about how three concepts relate to one another. Okay, so here's what we want to be doing for the rest of this lecture. The first question we want to ask and answer is, what are regressions and means difference tests, and how do we generate hypotheses using them? So we're going to look at some examples of real-world political problems and ask how we might use these statistical tests to look for patterns and test hypotheses. Second, we're going to ask what a confidence interval is and how the fact that statistics are probable matters for us interpreting statistics when we see them in the real world. And then lastly, when do we know if a statistical measure proves that a hypothesis is true? When do we accept the statistical measure that we're given? Okay, so let's start with a little bit of terminology here. What is a regression? A regression is just a mathematical model that tells us the average effect of a change in an independent variable on a dependent variable. For example, for every hour that an average student studies, how much do their grades go up? You can measure this. As a line, right? Sort of a basic slope-intercept line, right? For every hour, in this case, that a student spends studying, the GPA rises by 0.5. But this is not how we're actually going to observe the data, right? The students aren't going to fall into a straight line because studying, we all know, isn't the only reason that student grades vary. What we're actually going to see are the data points from the actual students, right? And we see that there are some students who achieve more than what their studying would predict and other students who would achieve less. The regression uses a complicated equation to calculate a line that finds its way through all of these points. And the way that it calculates the line is by minimizing the total distance from the line to all of the points. And the slope of this line, we say, is the average effect of the independent variable on the dependent variable. So if we were to actually have these students that whose data we gathered and then we created a regression line from that, we would then say that the average effect of studying on the average student is 0.5 points in your GPA, or half a point on your GPA for 1 hour spent studying. Notice now we can return to our hypotheses, right? We predicted that students who study more would perform better, but now that we have a regression, now that we know that we're going to ask about the slope of the line, we can change our hypothesis. In this case, we would hypothesize that the relationship between hours studied and GPA will be positive, right? We expect that when we gather all of the data from all of the students, that on average, students that study more will perform better in their GPA, right? We run the data. Is the average relationship positive? Yes. The hypothesis is true, and therefore we have evidence that our theory is right. Studying does affect grades. The more you study, the more you are or the better you're likely to perform. Okay, I have promised that we'll not see any statistical terms on the exam, but regression provides a good example of the type of term you might see on the exam. So let's do this as a potential exam question. Here's like your B-level answer. A regression is a statistical test of a hypothesis. Measures the average relationship between a dependent and independent variable. It looks like a line on a graph. If you write out this answer, I know that you've got the basics here, and you're definitely going to earn a B for this grade. Notice here that we've added some information, right? Regressions may also include control variables that eliminate the influence of competitive causes. We'll talk about this a little bit more as we move along. Okay, a means difference test. Means difference tests is just a different way of running the same numbers to see if there is a relationship between an independent variable and a dependent variable, and to see whether that relationship matches your hypothesis. So a means difference test describes the difference in the value of the dependent variable for two groups of observations. So for example, if we were to break students into two categories, those who study and those that don't. We pick a number of hours per week of studying that we say makes you a studious student versus a slacker. Then what we should see is that the students who study a lot have a higher GPA than the students that don't. This time, right, we might break down our data into two columns, right? Here on the left, we've got the students who don't study that much, which I've termed less than 3 hours a week. And then on the right, students that do study a lot, which is more than 3 hours per week. And what we would do is add up all of their GPAs and take the average and see whether the students who studied more, or the high studying student group, performs better than the low studying student group. Again, we can change our hypothesis, right? From our base hypothesis that students who study more perform better, we derive a new hypothesis. The average grades of students who study should be higher than the average grades of students that don't, right? So again, we're tailoring our hypothesis to the way that we plan to analyze the data. And when we run the data, we find that the average GPA for studious students is higher. So yes, the hypothesis is true, and therefore we have evidence that our theory is correct. Okay, so we've talked about a couple of really basic statistical tests: a regression, which tells us what the average effect of studying is, and a means difference test, which tells us whether two groups of people, grouped by their values on an independent variable, experience an average different outcome on the dependent variable. Now we're going to talk about statistics being probabilistic and a handful of concerns that we have when we take statistical measures. Okay, so first, one of the problems that you first need to think about when you're presented with statistical data is, are the observations that we gathered representative? This is known as selection bias. Here's an example of selection bias. Hopefully some of you recognize the person who's in this photo. I don't know how much American history you've had, but the person who's in the photo is Harry Truman, who became president of the United States, and he's triumphantly holding up a newspaper that predicted his defeat. The reason that newspapers were so certain that Harry Truman was going to lose a presidential election that he ultimately won is because the Literary Digest, a very influential magazine in the United States at the time, made what was one of the first early modern attempts at a representative survey of the United States to see who people plan to vote for president. So Literary Digest chose something like 16 states, and they drew 100 or 150 people in each state randomly out of that state's phone books, and then they called those people and they asked them who they planned to vote for president, and the people who picked up the phone overwhelmingly said Dewey. Now you'll remember when we talked about Afghanistan and my research design of knocking on doors and asking the people who answered the door if they had voted, there was a bias that was introduced because men are far more likely to answer the door in Afghanistan than women are. Well, in this case, Literary Digest got something else wrong. At the time that they did the poll, only about 40% of Americans had a telephone and a registered telephone number. And those Americans obviously were on average richer, and the richer Americans were on average more likely to vote for Dewey. So even though the Literary Digest poll predicted that Dewey was going to win in a landslide, Truman won in a landslide. And the reason that the poll was wrong was that the sample that Literary Digest took didn't represent the people that it actually needed to predict from, right? So one of the things that you might ask when you're provided with statistics is whether those samples are representative. One place this happens all the time, right, is that cable news shows love to run their own polls. Fox or MSNBC will ask viewers to call in and respond to some question about whether Donald Trump is doing a good job. Not shockingly, when Fox runs these informal polls, the president's approval rating is always very high, and when MSNBC runs these polls, the president's approval rating is always very low. While polling Fox News viewers provides a biased slice of American life, so we shouldn't take those polls very seriously. Another problem we might run into is that our independent and dependent variables are being caused by some greater thing, right? We call this spurious causation. Let's take a look at an example of spurious causation. This is a chart that shows the actual violent crime rate and actual ice cream sales in Dallas, Texas in 1998, you'll see that the correlation here is actually pretty close. It appears that violent crime and ice cream sales are closely correlated. So if we had a theory that violent crime, committing a violent crime causes you to crave ice cream, or that eating ice cream made you want to commit a violent crime, this correlation would stand as evidence for those theories. But of course we know what the real cause is here, right? Violent crime peaks in the summer when it's hot and people are short-tempered and irritable. Ice cream sales also peaks in the summer when people are short-tempered and they want a cool treat, right? Here's a more political example. There were a lot of theories in the 1970s that revolutions happened in countries because people were poor. They predicted that poverty led to civil war, and they sort of set aside the idea that revolution had anything to do with the quality of representative governance. People weren't rebelling against dictators, they were rebelling against being poor. But of course, undemocratic governments, dictatorships, are probably likely to make bad economic policy, and they're likely to tick people off. So you end up with this potential problem here. You see a correlation between poverty and civil war, but it's possible that that correlation is actually being driven by how crappy the government is. Okay, it's also possible that this spurious correlation problem leads you to not see, or selection bias problems as well, lead you to not see correlations that should be there. Here's a potential example, right? Government job training. Many governments, including the United States and most states in the United States, offer job training programs to people who meet certain criteria. But non-experimental studies have often shown that people who participate in government job training programs earn less than people who are demographically similar, right? If we pick people who are the same age, race, gender, socioeconomic status, educational attainment, what we find is that people who participate in government job training programs earn less than the people who didn't. So does that demonstrate that these programs are a failure? Of course not. This is probably selection bias. People that participate in these programs are less qualified in ways that the demographic information doesn't capture. They have some sort of an arrest record that makes them less employable. And so they join the government job training, and whatever the bias from their past is that caused them to participate in the job training continues and forces their income down. Here's another example, classroom size, right? We often hear that smaller classrooms must be better for learning, but again, non-experimental studies show that there's no correlation between classroom size and student achievement. So can we then just fire a bunch of teachers? Do we think that this is a safe way to go? Well, the problem here, potentially, is that worse students are put in smaller classrooms by teachers. Teachers see students that are struggling, and in order to help them catch up, they put them in smaller classrooms where they get more one-on-one attention. And so in this case, the correlation, or the lack of correlation, between class size and achievement is actually caused by something that's happening behind the statistics that we're gathering. Okay, so now that we've talked about a couple of ways in which we might gather statistics or interpret statistics badly, we need to tackle a final problem here, which is that statistics themselves are probable. Even when you do everything right, it's very possible that you will get statistics that appear to be misleading. Here in this example, I'm using UCSD students. I guess the last time that I taught this class must have been, or this lecture must have been at UCSD. But let's say that what I'm really interested in finding out is the average height of a student at Mesa. Now, we know a bad way to go about this, right? If I were to attend, say, a basketball practice, a men's and women's basketball practice for the Mesa team, and I took the heights of the average basketball player and presented that as an estimate of the height of the average student at Mesa, you'd know that I had overmeasured the students, right? We would know that my estimate was probably too high. A better way to do it might be to draw 10 students at random using student IDs, take those students' heights, and provide that as an estimate for the average student at Mesa. You might think, though, that it's possible that I would draw 10 very tall students, or 10 very short students, or 8 very tall students and 2 very short students, or some distribution of students that were not, in any event, near the average. 10 students isn't all that many, right? Here's another way to think about this. Imagine, for example, that I told you that I was going to flip a quarter 10 times, and that I would give you $100 if you chose the number of heads correctly. Most of you would probably correctly guess that the best choice in this situation would be to guess that I was going to flip 5 heads, because the chances that I flip a fair coin on heads or tails is 50-50. But you wouldn't be surprised if I flipped 4 or 6 heads. You probably wouldn't even be surprised if I flipped 3 or 7. 1 or 9 might start to look a little bit fishy, but you know that if I flip 10 coins enough times, at some point I'm going to get 10 heads and 0 tails, or 10 tails and 0 heads. So in other words, it's possible, if you see this little dot over here, that whenever we sample for statistics, we've somehow gathered a group of observations that are close to the maximum or minimum of the distribution, and we'll report that as the average and end up being really, really wrong. So what we should do to fix this in principle is to sample a bunch of times. We flip a coin 10 times, and then we do that again and again and again, and we see every time we record how many heads that we get. And over time what we see is that the number of heads that we get clusters around 5. If we were doing this exercise in class, I'd actually have you flipping quarters, and the vast majority of the time when you have classes that are over 15 or 20 students, you end up with most people flipping 5s, and you get some 4s and 6s and a handful of outliers. But what you typically see is what's known as normal distribution, right? We get a pattern of samples that clusters around the average, and then we know what the true average is, not because any one of our samples represents the average, but because we know that over time these averages are going to cluster near the true average. This is known as the central limit theorem, right? So because the errors in our measurement typically distribute normally, we can use the shape of this curve to determine the chance that we'd be measuring something out here, right? If the true average is 5'7", what are the chances that we would measure someone at 5'9"? So if we switch the logic a little bit, we say that the central line is what we measured. We have a sense of what the likelihood is that the real average height is somewhere way out here, right? And so this allows us to create what's known as a confidence interval. In this case, we can say with 95% confidence that the real average height is somewhere between the two red bars, because it's really, really unlikely that if the true average was somewhere out here in the minimum or somewhere out here in the maximum, that we would have measured this average height. If anyone has questions about how you do this math, we can talk about it, but the basic intuition is that the greater the number of people or observations that you take, the more measurement you have, the less likely it is that you're going to find something way, way out here, right? Go back to our height of MESA students example. If I draw one student and measure that student and report that as my estimate of the height, well, you know that there's a good 25% chance that I've picked one of the 12% tallest students or 12% shortest students, which means there's a 25% chance that I've really screwed this up. If I choose 10 students, it seems much less likely that I'm going to choose 10 extreme heighted students to one end or the other at the same time. Now say that I choose 1,000 students. Right, the likelihood that I'm going to get the tallest 1,000 students is starting to get really, really small. And so we know then that we can push these confidence intervals in, and the band around our confidence interval becomes small, and our estimate becomes more and more likely to be closer and closer to the true average. Right? With a 99% confidence interval, where we push it way out, we know that the real average height is somewhere between these two red bars. We see this confidence interval all the time in polling data, for example. It's down here. Okay, so why does this matter for testing hypotheses, right? We know that statistics are probable. We know it's possible that we don't have the real negative opinion of Trump or Clinton shown in this report. But why does this matter for testing hypotheses, right? Let's say that you have a theory. I don't know what this theory is, but that theory predicts that the average height of a Mesa College student is 5'7" or higher. You go out into the world, you choose your 120 Mesa students at random, and you measure an average height of 5'8". Sounds like you're in good shape, right? But depending upon where your confidence interval falls, you may still have a lot of error, right? If the real average falls inside the yellow zone, you're fine. You've actually measured a height of college students at Mesa that does support your hypothesis. The real student height is higher than 5'7". But if there's a 35% chance on this chart that you've measured 5'8", even though the real average is something below 5'7". So your measurement is in error, and that's giving you a false positive on your hypothesis. So when you see statistics reported in this way in these papers, they give you a sense of how likely it is that the measurement that they took could really be measuring a real average that falls outside of the predictions of the hypothesis. Let's consider the means difference tests now. Right, we predicted that the group that studies would have higher GPA, and let's say that that's what we measure, right? We measure that the group that studies has an average GPA of 3.4, and the group that doesn't study has an average GPA of 2.9. Now, what we want to make sure is that we didn't just randomly select a group of smarter or wealthier or mentally healthier students that study, right, that just happens to have a higher GPA than the students that didn't study. What are the chances that we just picked some people at random and that this difference isn't true? Well, now we have two confidence intervals and two distributions, right? We can see the chances that the lower studying group has a higher, in fact, has a higher GPA than the higher studying group. Anything in the yellow box and our hypothesis is maybe false, even though we measured and reported it as true, right? Here we can see that there's like a 99.99999% chance that Trump's negative rating was higher than Clinton's on the day that this poll was taken, right? With a 2.2% margin of error, what we know is that it's 95% likely that Trump's real negative opinion characteristic was somewhere between 59.8% and 64.2%. And Clinton's then was somewhere between 37.8% and 42.2%. We can draw these same confidence intervals around a regression line, right? The slope of the line has a confidence interval. If what we measure is a relationship between hours studying and grades, it's 0.5. It's possible that somehow we gathered a group of students who's unrepresentative. By sampling randomly and doing everything correctly, we still gathered in a group of students that was that's not representative. So the true slope of the line, the real underlying average of the students, might be anywhere between these dotted lines, and so therefore the true slope of the line might be anything that fits in between these dotted lines. Now, if our prediction was that the line should be positive, that the relationship should be positive, then what we want to make sure is that there's no way to fit a completely horizontal line in there, right? If we measured the blue line, but it's possible, it's more than 5% possible that the measurement of the blue line means that the red line is the real population average, then we can't tell for sure, right? We went out and measured, but we cannot reject the hypothesis, in fact, that there's no relationship between studying and grades. Okay, so to review, this organization, this way of laying out papers, makes managing some problems related to statistics, related to causal inference, related to selling the idea that your operationalization of a variable is good a little easier. You motivate your audience with a big question. You explain in detail all of the theories that might affect the outcome that you care about. Then you explain to your audience what things we would observe in the real world only if each theory is true. Once your audience understands the concrete steps you need to measure these observations, You do this by explaining why you've chosen to work in a certain place or how you're going to measure these concepts. Then you can go on and test the hypotheses and see which of the theories that reflects your big question is true. Okay. Let's not talk about external validity. We're not going to worry about that for the purposes of this class. So that's where we're going to end this portion of this, or this lecture for now. I'm going to start in very briefly on the Abrajano and Haenel reading so that we can have a head start for Wednesday's class. So I'll just close out of this guy really quick. And here we go. Okay, so for the next 2 weeks, we're going to be talking about some relationships and some theories that surround immigration and immigrant integration into their host societies. These are very politically contentious questions. We argue a lot about immigration and the right amount of immigration. We argue about what sorts of immigrants are good for this country and these kinds of things. So the 2 readings that we're going to tackle this week and next are really about measuring some of these consequences and testing some theories about our intuition of immigrant integration. First of these readings assigned for this week are a couple of chapters from White Backlash, Immigration, Race, and American Politics by Abrajano and Haenel. So let's start off here. We want to start off by thinking about what the big question of the piece is, right? So Abrajano and Haenel have offered us a gigantic puzzle. What is that puzzle? Take a second to predict what's going to be on my next slide. What are the political consequences of immigration is one of the big questions that the authors want to tackle here. How does immigration change our politics? Second, do patterns in immigration and media coverage of immigration change attitudes, change political attitudes, change what party you're likely to vote for? Third, do attitudes about immigration affect party affiliation? Do we change our parties based upon our attitudes towards immigrants? And lastly, do attitudes about immigration affect preferences for other policies, right? If immigration policy affects party choice and voting behavior, it's possible that these attitudes about immigration will change health policy and education policy and foreign policy, policy about abortion, policy about gun control. Many of the policies that we experience in the United States might be chosen by accident, and they're chosen accidentally based upon the response of the average American voter to immigration. So how could we go about theorizing how people respond to immigrants, who these people are, how their vote choice changes depending upon their exposure to immigrants, and what that means about patterns in politics in the United States? Now that we've asked our big question, we want to go through our lit review, right? We want to review the potential explanations here, the potential answers for how immigration affects politics. There are a few potential schools of thought on this relationship between immigration policy and the policy outcomes in a country or the country's voters' party identification. They break into 2 major debates. The first debate asks about the relationship between party policies, party preferences and policy preferences, right? They ask which comes first, and here are these 2 theories. The first theory is known as the Michigan School. The Michigan School argues that party affiliation is psychological. It's part of our identity. We think about being a Democrat or we think about being a Republican in the same way that we think about being French or Mexican or Catholic. These are parts of our identity that are deeply ingrained from childhood, and they're really very rarely flexible. People change their party affiliation about as often as they change their own appraisal of their nationality or their sexuality or what class they belong to. These sorts of things that are really, really deeply ingrained in who we think they are, or who we think we are, I'm sorry. In opposition to this is what's known as the Downsian school. The Downsian school argues that people pick their party affiliations rationally. They have some core set of policy preferences, outcomes for society, values and morals about politics that they prefer, and they take a look closely at party platforms, and even if they make some shortcuts when they vote for individual elections, they choose their party affiliation based upon how closely each party adheres to the voters' preferences for core policy. Okay, so there's a lot of complexity that Abrajano and Hanel don't cover when it comes to the second set of theories here. Okay, I should backtrack just a second. The first set of theories, those that are listed in blue, are intended to provide opposing viewpoints for how people choose their parties, right? The Michigan school suggests that this is mostly an emotional response. The Downsian school suggests that there's a rational choice happening here. The next set of theories that Abrajano and Hanel need to consider is how people respond when they meet and speak with or get to know immigrants. So the two potential theories here are the anxiety theory, which suggests that people become nervous when they're exposed to immigrants. You see immigrants moving into your community and you fear that they're going to change the character of your community in some way. And that fear actually drives you to become more anti-immigrant the more immigrants you're exposed to. The opposition to this theory is known as the contact theory. The contact theory, as it says, suggests that as people are exposed to immigrants, they become more willing to accept them. They understand that these people are part of their community, and they understand or see that the differences in culture that they bring in are either neutral or enriching, right? You might imagine that the anxiety theory and the contact theory are triggered under slightly different circumstances of what we would call exposure to immigrants, right? The anxiety theory sort of calls to mind Clint Eastwood rocking on his porch, and the Vietnamese are coming to town, but he doesn't actually speak with very many of them. He just knows that his neighborhood is changing, and the more of these people he sees, the more skeptical he becomes. Whereas the contact theory of immigration suggests, your neighbors move in from a different place, and you have them over for a barbecue, and you find out that they grill meat slightly differently than you, but you're all interested in drinking a good American light lager, so everything's happy. But again, we've sort of got opposing viewpoints here. Now notice how rational or logical each of these theories sounds on its own, right? When you listen to the logic of the Michigan school, people are born into families that are Republican or Democratic. They have very early childhood experiences about what those party affiliations and labels mean, and they attach that label to themselves somewhat emotionally, and they're unwilling to let that go without a fair amount of stress. That sounds reasonable, right? I mean, you probably know people who seem to be dyed-in-the-wool Republicans or dyed-in-the-wool Democrats because of something about how they were brought up. That being said, the Downsian school makes an equal amount of sense, right? Think about how you pick parties, or think about how you pick candidates. You choose people who either you agree with their policy positions, or you learn something about their character, or you observe their body language, and something about that person or that party resonates with you, right? You want to think that you've rationally derived your preferences from some core set of policy beliefs, your party preferences from a core set of policy beliefs. So both of these theories sound logically plausible, and what we need to be doing is thinking about ways to test between them. Similarly, this question of how we react to immigrants, or how native-born Americans react to immigrants, also both sound kind of plausible, right? We can imagine a world in which seeing a neighborhood flooded with new immigrants who speak a different language or have a different religion or a different culture might make the residents anxious. We hear these narratives in the news all the time about white communities that are flooded with immigrants of Asian or Hispanic extraction who feel like this is changing the character of their neighborhoods, and they become increasingly nervous. At the same time, we're probably also sympathetic to the idea that meeting and discussing with people and talking with them sort of exposes a common humanity. And anyone you can share a few laughs and a beer with is someone that you can get along with despite all of your other differences, right? So in order to think about how immigration is affecting party preferences and policy patterns in the United States, we need to ask ourselves about the average effects and how we might test for the average effects between these things. And part of the reason that we're reading these particular chapters of Abrajano and Hanel is that I think that when we get to the testing section, the way that they've attempted to parse out how Americans are responding to immigrants in their midst is actually really clever. They make some really clever predictions, and they use the data in a way that's clever and convincing to demonstrate that the average American, or in this case the average white American, responds in a particular way to immigrants that affects their party choice, and then ultimately therefore affects downstream policies, right? We elect Republicans or Democrats from certain districts because those districts are either anxious about immigrants or optimistic about them. And as a result, we see different patterns in things like gun control or healthcare policy that have nothing or little to do with immigration. And when we come back on Wednesday, we're going to spend some time talking about Abrahano and Haenel's intuitions about where this is going, and then we're going to spend a bunch of time talking about their tests. Oh, I totally forgot to ask you guys for an attendance question. Now that you've gotten to the end of the video, if you could please email me at john.porton@gmail.com and tell me what your favorite book or poem that you were forced to read in high school was. I will count you as having watched the lecture. Okay, hope that you've had a great weekend, and I will see you all on Wednesday.